Hi everyone, my name is François Belliti, and today we're going to talk about state spaces and search algorithms. And so we consider a very simple setting in which, for instance, we want to have an AI that's going to guide Pac-Man through a maze. So you have this grid, you have our Pac-Man, right? And Pac-Man wants, for example, to go to a certain point of the maze. I mean, that generally doesn't really happen in the game, but that could be an objective. It may want also to, grab a couple of pallets, and finally, may have to avoid, a couple of ghosts. And there are many ways we could try to solve this problem. In AI, what we're going to try to do is to solve it with a very principled and rational way. And therefore, it means that we have to start, if we want to solve anything about this environment, with a model of the environment that's going to be encoded in the artificial intelligence we're trying to build here. So that means that we need a state space. So that's something that's going to encode the properties of the space we are, exploring right now. So there are many possibilities open to us. So the first the first element we need in this is to have a goal. If we want to do something rational, there is, a rational objective we want to achieve. And in this game, it's fairly obvious. You may want to get as many pallets as possible in the shortest time, but you must keep in mind that in other settings, well, the goal can be much less obvious, and it becomes very helpful and useful to determine explicitly what your goal is. So keep in mind that we need a goal, we need a successor function, and it is related to states. So a state is just a way of encoding the current situation of the environment at a given instant. So right now I'm in this room and I'm standing at a certain location. That means that the environment is in a certain state. So if I move, one of my arms, I'm going to change the state. If I move around and I change my location, well, you will see that I will also change the state of the environment, right? So that's the kind of things that I can do, and because these things change the environment, because they are dynamic, they are encoded in the state. However, things that are constant, so for example, the fact that there is gravity, so I'm going to, stay on the floor here, or the fact that I cannot, walk through this wall because I'm going to hit it, these are constants that are going to be encoded in the successor function. So keep in mind that you will encode these constants that don't change about your world. So for example, the shape of the grid here, the exit point in the successor function, and all the things that are dynamic, so the different locations of the ghosts, of the pallets, your location, all of this will be in the state. Okay, so that's the first thing that we need to do when we're trying to solve a problem. Obviously, we need a way to represent it. So that's basically the main distinction between the successor function and the state, what doesn't change and what will change. And typically this you don't necessarily explicitly know it beforehand, but that's an oracle that's always available to you. So to a certain extent, you don't need to really instantiate that. The game is going to give it to you. This is where you will have work to do, and you will have typically to find ways to encode this state in a smart manner. So typically, you will have to represent such a state in memory. And that leads us to, data structures to represent the world. So for now, if we consider the simplest setting of this game, we can just consider that there is just Pac-Man, and we forget about the pallets and we forget about the ghosts. There is only one thing we need to keep track of. It's the coordinates of Pac-Man. Okay? That's our state space representation here. You can see that typically we don't even need this here. It's just a pair of integers. Now, if we want to keep track of the pallets, well, for example, we could have, a list of coordinates of the different pallets we have. Okay, so now you can see that there are many more different combinations now that can occur. Finally, I can also add, the state of the ghost. So I'm going to expand this pair to a tuple, and I will have coordinate of the first ghost, coordinates of the second ghost here on my picture. Okay, so that's how this problem will be encoded in the memory of our laptop, for instance, or our supercomputer. We need to have a formalization, basically, of the world that will quantify it. And keep in mind that there are a lot of things that can go wrong if we have the wrong representation here. That also there are a lot of optimizations you can bring to this representation. When you're talking about coordinates and, for example, you want to keep track of things in space, well, lists may not be the best solution, okay? You may consider arrays of booleans, you may consider what are called, spatial trees, so things like quadtrees, R-trees, and that's where a lot of work, comes in. Also, if your representation of the world, if the model you have is not accurate, obviously you will run into many different issues. So let's try ways to have, to step back a bit about our problem and check that, everything makes sense once we have encoded the problem in a program. So representations, well, we have, for instance, here when we try to keep track of the palettes, multiple options available to us. As I said, well, we can keep track of the pairs of coordinates as a list, okay? Oops, that's an X. But we could also do something different, because in fact here we're not exactly tracking each palette individually, we're just interested in the fact that, there is that combination of palette here on the board. So what we can do is have a double array of booleans. Okay, so depending on the problem you'll have, you need to consider, both options, and you need to consider two things. The first one is the size it will take in memory, and the second one is also the access time. Okay, that's going to determine how easy it will be for your CPU to, make decisions based on this representation. So I said the big word here, it's decision. So we have this world, and we want to be able to solve the problem, which is, for example, going to the other side of the maze without encountering a ghost. And when we explore this world, there are multiple strategies available to us. So that's what we're going to talk about now. We're going to talk about search. And search is basically searching for a way to achieve the goal. So when we conduct search, in fact, we may not need to know the goal ahead of time, okay? All that we need to do is to be able to test if a state is goal. Okay? So, whoops. We just need that oracle. The other oracle that we'll have is the successor function, and then the states, so how we represent them, and also how we choose a certain state for exploration. Well, that's going to be up to us. And there is, if you think about the way we can represent a problem, a fairly obvious thing that appears when we explore different options. So we start somewhere. That's our initial state. And we call this successor function, okay? So when we did that, we moved, from a single possibility. We knew we were there, and we didn't know how to go from there to the goal, to new possibilities open to us, okay? And if we choose to try out what happens if we expand, that state, we have even more possibilities, okay? And so on and so forth. And maybe at some point, we'll be lucky, and we will find that the state we reach here is the goal, okay? So obviously here, you want two things. You want to be able to reach the goal, because after all, that's what we're trying to do here. The second thing is that you don't want to have to deepen, that exploration too much. So here we have a tree, okay? We explore the world as a tree of possibilities that open themselves to exploration. And obviously, we are searching for a goal, okay? That's what we said so far. So that's called tree search. And that's going to be a meta-algorithm that's going to enable us to explore an unknown environment and hopefully reach the goal we're trying to achieve here without spending too much time exploring. So here you saw that there was already a lot of this meta-algorithm when I very naively expanded these possibilities. So what I did here is that I first expanded the start node, and I had the new possibilities that I had not yet explored available to me. What I did is that then these would be the topics of interest for me, the opportunities of interest. And this fuzzy concept is in fact narrowed down and called the fringe. The fringe is the set of states that you have expanded, so you know they exist. You don't know what's after them if you were to expand them, so you would have to call the successor function to determine that. And it's also, you've also eliminated all the states you've already explored. So for example, here I've already explored the start. It's not part of the fringe. It's passed. I know what happens there. And so the fringe is going to be this frontier, which is going to change. So for example, here, if I choose to expand this node, I'm going to get rid of this node because I know, the outcome of the expansion here. And that's going to be my fringe. But there's something that's still true about my fringe. It separates what is known and explored from what is unknown. And in fact, from the point of view, of somebody who's trying to solve this problem, these nodes have not been explored yet. So in fact, I don't even know they exist. I don't even know that the goal is here, okay? So this is completely unknown to me. And here I chose to expand this node at random. So here I have a meta-algorithm in that it's going to change depending on the strategy I will choose for the selection of the next node that belongs to the fringe, and I will expand. So it's all determined by who I will select next to call the successor function upon. Okay? Let's start with a couple of strategies for exploration. So first, there is an algorithm you've probably seen already. The first way to expand these nodes and to decide what to expand this is to do depth-first search. So I have my tree. I don't know yet that these different states exist. I'm going to find out. And the way I'm going to explore that is by a very simple recurrent algorithm. I start here. I'm going to get rid of the start. I'm going to expand it. This is going to be my new fringe. And then I will say that it's the last node I have added to the fringe that I will expand first. This means that I will store my fringe as a last in, first out queue. And here there is a nice duality between the data structure I will use to store my fringe and the nature of the tree search algorithm that will be used here. So if I expand the last node I have added here, it will be this node, for instance. So if I go from right to left. So I start expanding this node. I call the successor function on this node. I get rid of the node. It's no longer part of the fringe. And the successor function tells me that, well, the two new nodes that I discover are these two here. And I will do exactly the same. I will, take the last node I have added to the fringe, and I will expand it. And as you will see, I will expand the nodes like this, okay? I will deepen my search, always in the same direction on the tree, and eventually, maybe, I will reach the goal. So in fact, you can prove that if you have a finite number of states you can expand, and there are no loops, typically, well, this is a complete algorithm. Because what's going to happen is that at some point, maybe, you will not have found the goal, and you won't be able to expand anymore because, for example, you've reached a corner. So you will just forget about this path that you've instantiated, and you will start from the last node you've considered in the fridge and expand this thing. And at some point, if you have a finite number of states, well, it's clear that eventually you will find the goal. Okay, so the finiteness assumption here is pretty important. So that was for DFS. Here it's pretty clear also that this algorithm won't necessarily be optimal. So what is that exactly? Well, I'm going to explore with a rule that's not based on the time that is going to take me to reach the goal. And here the time being counted in the number of steps that are necessary in your exploration. Typically what can happen is that if the goal is here on the rightmost part of this tree, I will have to go through all the different nodes in the tree before I can discover that the goal was there on the right. So that's a problem, and this is not, therefore, an optimal algorithm if the metric you use is that of the number of steps that you need to expand before you discover the goal. So DFS, simple. It gets there, but it could get there too slow. And in some cases, if you don't have a finite number of states that you can explore, you will never get to the goal in a finite time. How about we do something different, and instead of deepening the search and going one way without considering the other options that are offered to us, we instead keep track of all the options available that are still worthwhile considering, and we expand them. So here I will start with a very similar algorithm, which is that but when I'm at the start point, I don't have many different choices I can make. There is only one thing I can do. It's expanding the start node. So I've expanded the start, and now my fringe is here. And BFS is an algorithm where I will always expand the first member, the member of the fringe that was added first chronologically. This means that my fringe is going to be stored in a first in, first out queue. Okay? It's a minor change, but it will have tremendous importance regarding the properties of the algorithm in terms of optimality. So what will happen here is that I have added this node, then this node, then this node. So this is the next one I consider for expansion. I expand it. It's no longer part of the tree, of the fringe, sorry. These nodes become part of the fringe, and so on. I can do the same thing with this node. I will expand this two, and this node I will extend this two. So once I've done that, you can see that these nodes have been explored. The next nodes in the fringe are these folks here. And there is a property here that's pretty interesting. The fringe always occupies the width of the tree extensively. Okay? And also, all the nodes that are part of the fringe at this moment have the same number of steps to get through them. So at some point, say, I reach the goal. So for example, I have expanded this guy. It's no longer part of the fringe. Well, I know that any expansion here will result in a number of steps that will be, at most as, at least as many as number of steps that I have along this path. So this path, basically there is no way I can beat it if I expand any of these nodes because it's already taken me the same cost to get there in number of steps. And therefore it means that this algorithm is complete because unless I run out of memory, I will find the goal, and also it's optimal. If we count, if our metric is the number of steps required to get to the goal. So here you can see that it's not exactly as interesting as we hope this will be, because in the real world, in real world problems, all decisions are not associated with the same cost. So if I'm, for example, driving, it takes me, more time to choose a certain path, a certain, section of road than another section of road. And typically, I don't like to spend too much time on the road. So the cost I'm going to try to minimize is, the sum of delays that I experience. All right, so now UCS. So in UCS, things are going to be a bit different. I start at the same point. And now my successor function is not only going to give me the successor states, it's also going to give me the cost that's associated with reaching them. So it's actually quite a substantial addition to the complexity of the problem. And now when I keep track of the cost associated with going to a certain node, it will be typically the cumulative cost I will incur along the path to get there. Okay, so here typically it would be 12. To achieve this property of always being about as far away from the goal when it concerns different nodes of the fringe, I'm now going to have a modification of BFS which is going to be concerned with enforcing this property, but not in terms of number of edges expended along the path, more in terms of the cumulative cost I have incurred. And what I'm going to do is, for instance, I will have this fringe here. And instead of just having a queue to keep track of the nodes, I'm going to have something a bit different. So if I want to minimize the cumulative cost to reach the node, to reach the goal, the best candidate here is the one with the least cumulative cost. And therefore, I will choose to expand the best candidate. Select this node. Now the successor function informs me of the costs associated with the state transitions there. I have my new fringe. This node has been explored. Actually, I would have this node too, with a cost, for instance, of 11. All right. Now I can recompute the cumulative costs associated with going to this new node. So I do 6 plus 8, 6 plus 9. I get my new cumulative costs. And now I know that I have a new best candidate, which is the 7 here. And because I always select the best candidate to expand next, well, I know that there is no way these candidates here after expansion can beat this one if I reach the goal next. Okay? Because if I reach the goal here, and the cumulative cost is 2, I have changed my fringe to this. Now the fringe is here. And I see that the cumulative cost here is 9. So now the goal is selected for expansion. This means that there is no way I will be able to beat that path, because regardless of what I expand next, because the costs on the state transitions are always assumed to be positive, this cost is minimal. It's the best option that I can achieve. And to just keep track at any moment of the best candidate in terms of cumulative cost to reach a certain node, I will just change my FIFO queue to a priority queue. And the metric associated with the priority will just be the cumulative cost to go through a certain node. So this still has the completeness property of BFS, because eventually I'm going to expand the goal unless I run out of memory before the end, and it will also be optimal. So here, this is called tree search because, as you can see, there is no looping at some point in the tree. There is nothing like that. Okay? What could happen if you encounter the same node once again is that you could loop bad things could happen. This is called graph search. There is a very simple way of enforcing a fundamental property here that enables completeness, and that is to say making sure that there is only a finite number of options to expand. And a way to enforce that in the context of graph search is just to make sure that if you've explored something already, you're not going to add it once again to the fringe if the successor function invites you to explore the state once again. If you are keeping track of the costs associated to reaching the nodes, you're going to do the same thing, only this time you may reconsider a node for expansion if you found a better way of getting there. So if you find that you are going to re-expand, that you could re-expand the node, but this time with a lower cost, yeah, you should reconsider this option. You should add the node to the fringe. The thing is that with uniform cost search, because of that property that basically is that we've only selected the best option so far, we normally won't have to do that. So now that we have seen this theory of first how we represent the world and then how we think about it and how we explore options that are available to us, we are going to study practical instantiations of this. And in the meantime, we have a couple of minutes to think about a simple question. When is UCS, Uniform Cost Search, equivalent to breadth first search? All right, thank you. And now let's move on to the worksheet. Hi everyone, welcome back to Search, the first section of CS 188. So now we're going to apply search algorithms to actual problems, and this is important because it's going to tell us whether there is a bug in the algorithm. This is a good way to test your algorithms when you're doing an exam. The second reason why this is important is that this is going to tell you how you could perhaps improve a certain algorithm you've come up with. So let's start with DFS. So in DFS here we're going to add nodes in alphabetical order. We're going to add them to a stack. We add to the front of the stack and we pump from the front of the stack. So we start in S, we pop S, and then we add what we can expand from S, that is to say S to A, S to B, and S to D. Okay, and notice here that I keep track of the entire path because that's the solution that I'm looking for. I want to keep track of the path I need to follow to get to the goal G. So now I pop from the front of the stack, and this is S to A, so I look at the options that are available from the node A. I only have one, and therefore I add to the front S to A to C, and I keep S to B and S to D in my fringe. So now I pop the front again, okay? S to A to C. I have two options, and if I add them in alphabetical order, this is what I will add to the front of my fringe. S to A to C to D and S to A to C to G. I will still have S to B and, sorry, you probably can't see there, S to B and S to D. So this is still something I will have there. And you could say, well, I found G, it's okay, I'm done. So no, in these algorithms, we're only done when we expand from the goal. So we're going to expand again. The first thing we have in our fringe, and now we're going to find S to A to C to D to G. We'll still have the same elements as before, S to A to C to G, and S to B, S to D. Finally, we expand this, and we'll expand from the goal, so we're done. And this is the path that we found. Okay, so this is what will be returned by the algorithm. As you can see, basically we're going through these multiple costs. And even if in the simple number of steps we undertake to reach the goal, this is not optimal. Still, we found a goal. So here we can see that the completeness property of the algorithm guarantees that we do in this setting, and that's one of the first things you may want to achieve. So in BFS, as usual, we start from the S point and we expand it. But now our rule for what we choose next for expansion is going to be slightly different if we compare that to DFS. What we're going to do is that instead of popping from the front, we're going to pop from the back. And so the first thing we're going to extend here is S to B, which gives us S to D to G, and we add it to the front. So you start to see what's going to happen now. We have this basically rotation. We start by expanding X to B. This gives us S to B to D. We still have the other ones, S to D to G and S to A. Now we expand S to A, which gives us S to A to C. All right, so S to A to C, which we add to the front. And we still have the two other nodes there. And now we expand S to D to G. We expand from the goal. So we're done. We know that this is the path we're going to return. And as you can see, we didn't need many steps to do this. But the problem is that if we now want to take into account the costs on the edges, which are practically the costs of interest in real life. So for example, when you're trying to spend as little time on the road to get to a certain point, well, this is not going to be optimal. And we are going to study now our modification of this, so UCS, and see how it applies to this graph. All right, so now we're going to try to solve this search problem and take into account the fact that to each edge is associated a cost, and this cost can be different from an edge to another. So now we'll want to reach the goal starting from S. We want to go to G, and we'll want also to find a path that is minimal in terms of accumulated cost along the edges that the path is going to span. And before with BFS, all that we guaranteed was that the number of edges along the path was minimal. So when we do UCS, we expand the nodes by selecting on the fringe the one that has the lowest cost associated with. So we start from S, as usual, and now we add S to A, S to B, and S to D to our fringe, and we also take into account the different costs that we see. So we know that to go from S to A, the cost is going to be 2. To go from S to B, the cost is going to be 3. And to go from S to D, the cost is going to be 5. Now, we have a priority queue, and it's always going to select the element with the lowest cost. And this time it's going to return S to A. So S to A, we expand. We get S to A to C. And the cost is 2 plus 4, 6. We keep track of the previous elements in the fringe. So S to B with a cost of 3 and S to D with a cost of 5. And now we select the element with the lowest cost. So here is 3. I expand S to B. The only option is to go to D, and the cost will be 7. S to B to D, the cost 3 plus 4, 7. S to D. Now, who is the best candidate here in the fringe? It's S to D, so this is what I'm going to expand. And I'm going to go to G. So I'm going to have now in my fringe S to A to C, the cost 6, S to B to D with, so this is what I selected here for expansion. The cost of 7, and now I have S to D to G, and the cost is going to be 10. So who do I select next? I select the one with the lowest cost, so I'm going to select for expansion S to A to C. The two options available to me are, here the cost is 1, to go to D, or to go to G. So this is going to give me S to A to C to D with a cost of 7. Oops. And I don't know that I'm going to select this one or another, in fact. Then I'm going from S to A to C to G, and the cost is going to be 8. And I keep track of the previous elements So S to B to D, cost is 7, and S to D to G, and the cost is going to be still 10. Now, for expansion, I have a time. Here, I have a tie between S to A to C to D, which is this node here. The cost is 7. And I have a tie between this and S to B to D with a cost of 7. So here, in fact, the priority queue can return either this element or this element. And we have no guarantee on which is going to be returned. Practically, this is mostly going to be determined by the order of addition of the element in the priority queue, of insertion, sorry. So say that we expand, S to A to C to D. Here the only option is to go to the goal. Oops. And the cost is going to be 12. So I've selected this one for expansion. I keep track of the other elements. And here you can see that the impact of the tie is immediately limited, because the next element, the one with the best, is going to be S to B to D. Simply because here, as I have positive cost on the edges, I'm bound to expand this one next, the one I was tied with. So as you can see, this order of selection really doesn't matter for the algorithm. So S to B to D, I expand, I get a cost of 12. So now I go from S to B to D to G. So here I've reached the goal, but I'm not done because I've not selected this thing for expansion. Now, what I'm going to select for expansion is going to be the option with the lowest cost. And in this case, it's going to be S to A to C to G. So we select this for expansion, and because this contains the goal, we are done. We found the shortest path, and the cost is associated to 8. So here, two things were important. The first one, that we kept track of the costs. The second one, that we chose a data structure that has a certain contract with us to do so. So in this case, a priority queue. And what is really neat is that here, you don't really care how this priority queue was implemented for you. You use this encapsulation. All that you need to know is that is going to return at any point the best candidate for you. And this is going to enable you, probably, to find the path with the lowest cumulative cost on it. All right, so that was UCS. A heuristic is a hint. It's basically an estimation of how much it could cost to go from a current node to the goal. And you need something rather fundamental about your heuristic to achieve the best possible path. You need it to be admissible. What it means is that your heuristic is actually an optimistic assumption on how much cost you will incur if you want to go, for example, from A to the goal. So you don't know which path you're going to follow. You don't know that the actual cost would be, for example, if you follow this path, 6. You don't know that. You just have an educated guess, which is, well, it's going to be 2. And the thing you want about your heuristic is that it's over-optimistic. 2 works here because it's a lower bound to the path that you would have if you were choosing this option, so going to A. The reason why this is important is that being over-optimistic, if basically you track down the cost that is, for example, so the actual cost computed that it takes you to go from S to the current node plus the heuristic. If you do that, and at some point you find out that there was a better path to go to the goal, because the heuristic was over-optimistic, this is not too bad. You will still have optimality. You will just have, taken a bit more time to compute the solution, but the solution you find is still optimal. The problem, though, is if the heuristic is pessimistic, because then it's going to keep you away from some options that are, in fact, pretty good, and possibly you would have an optimal path there, and you're not even going to try and explore this. So that's the important thing about a heuristic. A heuristic is like a copilot. You want an optimistic copilot. Just remember that. You don't want C3PU on your side. You want, somebody super optimistic. So that's about the heuristic. And so then again, it's a fairly important aspect of search in practice. This is where your art will come into play. If you're good at finding heuristics, you're going to probably improve the practical runtime of your algorithm. And there are different ways of leveraging a heuristic. The first one is what's called greedy search. And here you're going to do something that's kind of like, UCS, so you'll have that priority queue, and the node that you will always select for expansion is going to be the one with the lowest heuristic associated. So let's try this out here. So we start from S, we expand, and again, we have A, D, and B as opportunities for expansions. So we have S to A, S to B, and S to D. And the heuristic costs associated with that are 2 for this one, 2 for this, no, 5, sorry, for B, and 1 for D. So if we follow the rule of expansion of the one with the lowest heuristic cost, we expand this node here. And that gives us S to B, S to A, S to B, S to D to G. Okay. And we reach the goal. The heuristic at the goal has a value of 0 because we're there. Okay. So we expand this guy next, and we found a path, which is a valid one, but not the optimal one. Okay. And the fact that we lost optimality is just due to the way we exploited the heuristic. Here we completely forgot about the actual cost we can compute about the path. We just, took an educated guess into account, and that's because this guess is not exact that we lost optimality. So now, how about we do something that's, as fast as greedy search, or at least that has this increased speed thanks to the heuristic, but is still optimal. And what we're going to do is A star. So in A star, we are going to prioritize over the sum of the actual costs from S to the node plus the heuristic. All right? And what you can see here is that, in fact, it's a lower bound on the total cost that we can get if we expand this path. So it's extremely reasonable if we have an admissible heuristic to take that into account to prioritize our queue for expansion. So we start again from S. We expand. We have A, B, and D. S to A, S to B, and S to D. The heuristic cost is 2 here. So we'll have 2 plus an actual cost of 2. This is going to give us a prioritization cost of 4. S to B, we have 3 plus 5. So let me get the colors right here. 3. So 5 heuristic plus 3 of actual cost, which is going to give us a cost of 8, or an estimated cost of 8. And finally, S to D, we have 4 plus 1. 1 being the value for the heuristic and 4 being the value for the path, the cost that we incur, and it's 5. So now if we select a node for expansion and the node is the node with the lowest expected cost, so in blue here we are going to select S to A, and then what do we find? Well, we have S to A to C. Now the estimated cost is going to be 2 plus the cumulative cost along the path, that is to say 6. This is going to give us 8. Now, we keep S to B and S to D. We still remember the estimated costs, okay, of 8 and 5. So the next node that we're going to select for expansion is going to be D. So we do that. From D, there's only G to expand. So we still have S to A to C. The cost that we estimate being 8. We have S to B with the same cost. And we have S to D to G. So here the total cost is 10. And well, we don't have a heuristic cost because the heuristic cost to the goal is 0. So now if we select a node with the lowest estimated cost for expansion, is going to be S to B to C. If we select the one on the left to break the tie, so we select this one. From C, there are two possibilities. So we can go to D. And now the cost that we estimate, the lower bound we get is 2 plus 4 plus 1 plus the heuristic. So it's going to give us 8. And we still have S to B with the value of 8 and S to D to G with a value of 10. Now, as you can see, because the heuristic was over-optimistic, it turned out that our estimate here has not changed. However, what has changed is the composition of the estimate. And so we have a 2 plus 4 plus 1, that is to say 7, of actually observed cost. And on top of that, we have the 1 heuristic cost. Okay, so we select once again this for expansion, and we add the goal. The estimated costs for the rest doesn't change. And therefore, here we'll have a total cost of 12. Sorry, C to G. 8. And this time it's an observed cost. We reselect for expansion. We break the tie by selecting the one on the left. And we expand from the goal. This means that we found an optimal path. Okay, so here you can see that basically the heuristic was pretty helpful in guiding our search towards where things could be good, and it turned out that, well, mostly they were, although the heuristic was not a perfect predictor of the actual cost to go from a given node to the goal. All right, so that was for search. Now let's see a problem that's more about how to model the world. So, welcome back, and this time we are going to study the problem 2, which is the Tower of Hanoi. It's a fairly well-known problem in CS. It's kind of a cool one because it has interesting structural properties. And the first questions that were asked were, if I remember correctly, so a state representation. So here, it's important to keep track of the size of the different tiles here. And the way we can do that is by numbering them, okay? So then what we need to keep track of is where these different tiles are located. So what we can do is have a first list for the leftmost pole. And at the beginning, it would contain 1 to n. And the list corresponding to the middle pole and the list corresponding to the rightmost pole, well, they would both be empty. So that's one thing. And by the way, that answered B, okay? That's the start state. For a given state, what actions are legal? Well, here the game says that you cannot take a tile and put it on a smaller one. So it means that if J is first element of a list, you can only add I that is strictly smaller than j. And basically that is going to condition your successor function. This is not part of the state space. It's a rule, it's constant, so it's going to be in the successor function. And finally, the goal state, well, it says that we want the different tiles to be all on the rightmost pole, and because they have to be in decreasing order of size, well, the end of the game, the goal will be this state. So that's for the description of the state space. Bear in mind here that this seems simple. In other cases, it won't be. In other cases, it won't be that simple. And also, if you're wrong encoding that rule, where it's going to get you a wrong successor function. If you have that, then you'll be in trouble because you won't be exploring the right states of the graph. So be careful when you model things. So now we are going to tackle the optional questions in the Tower of Hanoi. We know that if we want to be able to transfer all those tiles to the rightmost pole, well, necessarily we'll want to have the biggest tile there. And therefore, it means that at some point we'll have all the tiles but the biggest, on the middle pole, and all of this will be gone. All right. So once we are there, well, all we need to do is to be able to transfer these tiles on top of the biggest tile. Okay, so how can we get to this? So we start from our initial stack. We unstack it to the middle pole. We have the right to do it. We can take all those tiles until the n-1, put it on the middle pole, transfer the largest tile into the rightmost pole, and then we end up with that situation in which now we are completely free to move these around because they are all smaller than n. So n is pretty much in the part of the horizontal plate here. And now all we need to do is to be able to solve the same problem, only this time we only need to take into account n-1 tiles. And so basically what you can see is that if you're able to solve Hanoi of n-1, you're able to solve Hanoi of n. So let's just decompose this a bit. If we wrap up, we still need to be able to unstack these different elements on the middle of the board. And so it means that to solve Hanoi of n, we need to do basically Hanoi of n once, and Hanoi of n-1 once, Hanoi of n-1 twice, in fact, because we need it first to unstack all these elements to the middle pole, and then unstack all the middle to the rightmost pole. And therefore, we can apply an induction reasoning here to solve Hanoi of n-1. We need to know how to solve Hanoi of n-2, and etc. And if you keep digging like this, you will find out that eventually, as we know how to solve Hanoi of 1, well, we have a termination condition here. And overall, the number of calls, of recursive calls to answer the final question to the method is going to be in 2 to the power of n. So you can, what is nice is to be able to solve the problem by showing that in fact it's just the composition of smaller instances of the same problem. Note here that this is different from tree search. Tree search expands the world without knowing what's going to come up next, so it's very much forward exploration. Here we have an idea of how things will be if we want to solve this problem. We know that we'll be able to get there if we're able to solve the problem with n-1 tiles, and this is therefore a bit more similar to backtracking in a way. So this is not something that we can always afford to do. All right, so the final problem, which was also optional, the 15 puzzle. So here, what we want to do is sliding tiles until they are ordered in that manner. And so you can start, from a random state here, having completely unordered tiles. You want to get to this goal state. So here, it doesn't exactly look like a graph. However, because we're doing tree search, well, we're just going to explore, given a start point, the different possibilities available to us, given to us by this successor function, which says that we can only move one tile at a time in a blank space. And by doing that iteratively, eventually, we'll find if and how we can get to the goal. So here we're trying to build heuristics for the A-star algorithm because, as I was mentioning for the previous exercise, well, if you have good heuristics, it's going to considerably speed up your search. It won't change the optimality as long as your heuristics are unmissable, but it will practically accelerate the runtime. So how do we get a heuristic based on the number of misplaced tiles? So we know that a misplaced tile is going to have to be moved. If it doesn't, there is no way we can reach the goal. And this is going to take us one step. Okay? Cost 1. So we know that we have h, which is just the number of misplaced tiles. Why is this optimistic? Well, it's obvious in this game that to move a tile, you will probably have to move other tiles, and this is going to take even more steps. So this is just a lower bound on the number of tiles you will have to move, and therefore on the number of steps you will have to undertake to get to the goal. Therefore, this is an admissible heuristic. It's something that's optimistic. Now, the second question was create a heuristic using the Manhattan distance. Okay. So, as I was saying, when you have a misplaced, I can say this, tile, you will have to move it. You can also say that you will have to move it by a certain quantity. And you know that if a tile is misplaced, it will have to move to location in goal state. Okay, so basically, if you're looking at 12, it will have, if 12 was here at some point in the game, it will have to move there. And because this is a grid, you know that the distance that you will have, the number of elements of the grid that you will have to span is here 3 plus 1, so that's the Manhattan distance. So once again, for each time we have a misplaced tile, we're going to have to move. Well, that's one thing we know, but we're going also to have to move it n times, where n is a Manhattan distance to its location in the goal state, and that gives us, again, a lower bound to the number of steps we'll have to undertake. And because it's a lower bound, it's an admissible heuristic. So 3, we've proved that there are lower bounds on the cost we can expect. That's all we need to do. Now, 4, what could go wrong if you have a wrong heuristic? Well, the problem with a wrong heuristic, as I was mentioning, is that you will not explore elements along the optimal path. Or it's more accurate to say you may. No, if you're unlucky, that's what will happen. So let's build an example in which we have a heuristic that creates that issue. And something very simple, so let's say that we have S here. So that's a very simple example with graphs. So all right, so here I will create an example in which the heuristic value for A is 6. Here, if I do my expansion, I will go from S to G and A. and with a cost of 5 for G, and 1 plus 6 for A, that is to say 7. G will be selected for expansion, therefore I'm done. The problem though is that the actual cost, the actual optimal cost here is 2, and because I have a non-admissible heuristic, because here to be admissible I would need to have 6 lower or equal to 1, because I don't have this property here, I basically failed in finding an optimal path. Note though that we still found the goal, so we still have the completeness property here. Yeah, so that's it for the heuristics, so we need to be very careful that they are admissible. Generally, if you deal with geolocated data, well, the great cycle distance or the Euclidean distance are fairly good heuristics. Again, you don't need something that's exactly the distance, you just need a lower bound. As long as you have that, you're good. And also the Manhattan distance, well, if you're in Manhattan, is pretty handy if you're revving. So try to think about these simple heuristics. They're going to be able to guide your search better. So that was for state spaces and search. So keep in mind also practically that if you use an algorithm, you need to make sure that it has bounded memory. So don't go out in the industry and implement something like A* without making sure that it's a memory-bound version. If you're interested in that, I think you should take a look at so the Artificial Intelligence: A Modern Approach book. There is a very nice overview of these memory-bound complete and optimal algorithms, so modifications of A*, and that's a lot of fun taking a look into. All right, thanks everyone.